if we look at, these are really the two big rules when it comes to deciding whether your molecule is polar or nonpolar. So one, you have to have symmetrical molecular geometry, and we'll look at that in just a second. I'll show you the ones. Linear is one of those symmetrical molecular geometry. You know, humans just have this ability, I think, to look at something and say that's symmetrical and that isn't symmetrical, or that even possibly, you know, putting a fine edge on it in terms of linear, tetrahedral. Chemists do that, I guess, but you know, it's just it's a again, I think it's a skill that we all have, and here we're applying it to, you know, these little molecules, a little bit more abstract, but it's not too bad once you see the pattern that develops as you go through the list here. And then the other thing that has to take place if we're talking about a nonpolar molecule, and again, you know, these two rules here are just for nonpolar molecules, and if it meets these two rules, then it's nonpolar. Right? If either one of these rules are violated, then it's a polar molecule. So there's a sort of a clear line in the sand, if you will. If again one of the rules violated, then it's polar. So the second rule, all the atoms in the central atom must be the same. We'll apply this to the examples that we've been working on for this chapter. But first off, let me go through the symmetrical molecular geometries real quick. And this is the same table that we've seen before. And I'm just going to go in here and highlight those particular, and again, we're talking about molecular geometries that are symmetrical. Well, one thing to keep in mind is that the actually, I think that, hold on. Okay, I cleaned up the highlighter just a little bit so it doesn't blur from one to the next. So one thing to keep in mind is that it's all molecular geometries that we're talking about in terms of something that's symmetrical. And one thing to notice is that, you know, there's certain ones that, well, the overall geometry and molecular geometries are the same, and so those count as symmetrical structures. And also, if you notice, so if linear is symmetrical up here, then it makes sense for linear to be symmetrical down there. And then the other one to be aware of is the square planar structure. And so, like for example, a square planar example, just a generic, so some central atom there, and you would have, let's just use X's for atoms attached. So just looking at that, imagine that all 5 of these atoms are in the same plane. This is a very symmetrical, I guess I should do these as wedges, like they're coming out at you. This is a very symmetrical molecule. It's flat. All the atoms are the same around it. The extra little bit here would be the E2. There would be it would be a couple of lone pair electrons, one poking up and then one pointing down. So all in all, this is a very symmetrical molecule. So again, these are the symmetrical molecules that you should be familiar with. And let's just apply these two rules to the examples that we saw, or that we've been working on from the earlier slides, back up here with phosphate, starting with phosphate. And we can have nonpolar ions. That's really what we're saying. This is what's going to happen here. So nonpolar is really just telling us how is it symmetrical or is it asymmetrical shift in electron density. We're not necessarily saying whether it's a charge or not. Okay, so you can have nonpolar ions and nonpolar molecules in the context of how we're approaching this particular topic. So we apply the rules, and again, let's see. Here we go. There's a molecular geometry that is right. Tetrahedral is one of our symmetrical geometries, and you know, if we look at oxygen, all of those atoms attached to the central atom are the same. Therefore, this is a non-polar molecule. Actually, I'm going to change the ink so okay, so green will make it very distinct from all the other colors here. The PowerPoints I'm reusing on multiple videos, adding content, so I think it gets a little bit, messy. So, but anyway, okay, so here again we have an ion. That's fine. We can have polar or nonpolar ions. That's good. And it is a linear molecular geometry, just like carbon dioxide. So yes, it is a symmetrical molecule. And then both atoms attached to the central atom are the same, so therefore it is a nonpolar molecule. And again, applying the rule, once you have the structure done and the geometry correct, nonpolar versus polar is a fairly simple kind of a thing. Just if you can remember your symmetrical geometries and that kind of thing. So trigonal bipyramidal, remember, when the overall geometry and molecular geometries are the same, trigonal bipyramidal, octahedral, etc., then it is a symmetrical geometry. And then, yeah, all of the atoms attached to the thing are the same. So they're or attached to the central atom are the same. So it's our nonpolar molecule. And then the final example is this guy here. And again, we're going to apply the rule exactly as stated. We say that is this a symmetrical geometry? And yes, it is. A linear, right? Linear shows up in a couple places. If linear is symmetrical up here, then linear is symmetrical down there. So that's the first rule is intact, and then the second rule is intact. The iodine, they're the same atom attached to the central atom. Now this one has additional aspects. It's all the same atom, so that sort of adds, I guess, really to the non-polarity of it. But anyway, we're just applying the two rules, and the two rules work for us in all cases, essentially. So really, notice all of those examples that we've been doing are nonpolar molecules. So let me just take a minute here and talk about. Actually, let me go back to the table that we were just marking up. If I can find it, there it is. So with the symmetrical geometries. So one thing that this implies is that if for now polar molecules, one thing you can say about polar molecules is that these particular geometries, any of these geometries, no matter what atoms are attached together, essentially for us, we're going to treat those as polar molecules. Now I can envision examples where the or it's the same atom maybe, or the electronegativities are really close, and it may behave like a nonpolar, but I'm not worried about that. Okay, this is I'm assuming the first class you've ever come across this particular topic, and I just want to approach it from the simplest approach for distinguishing between polar and nonpolar, and also the one that works the best. It's the easiest one to deal with. What we just went over here, if you take organic chemistry, it's probably going to cover 95% of the examples that I can think of. So, and let's just sort of finish out some of the. I'm going to look at the big list here, and notice that what the slides are doing here for us is that they're already telling us what's polar and nonpolar. And if we look at these, so let's just sort of walk through these. This is the ones I'm listing here are the symmetrical geometries. So tetrahedral here and tetrahedral here. This is a trigonal pyramidal for ammonia here. This is AX3E. So it's one of those. It's a trigonal pyramidal. So like I said, for us, it's always going to be polar. And yeah, so it's polar. The other one, so we have all these other ones are symmetrical geometry. So again, they've met with the first rule, but notice that it's only these two that actually have the second rule intact, where all the atoms are the same. So in each one of these, and here you have chlorines all the way around. So in both of these nonpolar molecules, there's an equal distribution of the polar covalent bonds, I guess you would say. It's a very symmetrical shift in the electron density. And yeah, I mean, chlorine is really pulling electron density away from this carbon here, but it's doing it in a very symmetrical fashion. Therefore, it's a symmetrical molecule, it's a nonpolar molecule. Something like this guy, where there's just one chlorine atom. Now it's all, well, whopper-jawed. It's shifted in one direction way more than the other direction. And so now this is what, even though this has a symmetrical geometry, it's that one polar covalent bond that gives rise to the asymmetric shape of the electron cloud. So again, the first rule is intact. The second rule has been violated. Therefore, it is a polar molecule. Yeah, and again, if you do take organic chemistry, this is a topic that's going to play a big role in terms of understanding how things work in that particular class. So you may want to keep this hyperlink close at hand if you have to take that class. Okay, thanks.